Alright, so yesterday we came up with this supersaturation equation and found that it could explain why in a turbulent mixed phase cloud we can maintain liquid water for a long period of time, which is consistent with observations. So the Berger-Unfin Dyson process, which is about ice crystals growing at the expense of droplet, doesn't always act. It's not always true, because by growth of ice at the expense of droplets, that means that the droplets are evaporating, they're shrinking in size. However, one of the cases yesterday I showed had that the supersaturation, even though the cloud was mixed phase, the supersaturation remained positive. It decreased. At first it increased and then it decreased, but it always remained positive. And in that case, the liquid drops still grow. So the Berger-Unfin Dyson process, as written, doesn't always have to act. And this is a fairly recent realisation, I guess, which has changed the way that weather forecast models treat the mixed phase clouds in the weather forecast models. Right, so today I'm going to spend a little bit more time on this. We're going to delve a little bit more into it. To look at the supersaturation, I want to quantitatively analyse it, because it's by quantitatively analysing it, hopefully it helps us understand a bit more what it all means. And so mixed phase clouds, one of the things about this lecture is mixed phase clouds can behave very differently to ice-only clouds, because the liquid water is important to the cloud's properties, how the cloud interacts with radiation, the cloud lifetime, how long the cloud lasts, because if you have ice, you tend to get precipitation and then that's it. And also, another topic, which I won't talk about too much, but thunderstorm electrification, how we get thunder and lightning. Okay, so current thinking, and this, so there's a retired professor from University of Manchester who came up with this theory by conducting lab experiments. The current theory is that thunderstorm electrification is the interaction between ice crystals, so they bang into each other and they transfer charge, but that has to happen in the presence of liquid water. So you need mixed phase clouds for this charge transfer to be strong enough so that you can get the charge separation that will eventually lead to lightning. So mixed phase clouds are very important to thunderstorm electrification, which I won't go too far into the details of. It's a very important topic, I'm sure you imagine. What I want to talk about is a little, well, fairly big field experiment. I sometimes go here, Switzerland. It's a research observatory at the Jungfraujoch lab, which is here, based in this centre here. And it's at the top of the Swiss Alps. That's the altitude, 3,500 metres or so. And it featured in the film, I don't know if this might be a bit before your time, but the Clint Eastwood film, famous actor Clint Eastwood, called The Eiger Sanction. Okay, anyone heard of that film? I'm showing my age a bit there. It's probably a little bit before my time, if I'm honest, but I have seen the film. It's worth a watch. It's quite, I'm quite a fan of Clint Eastwood anyway. So you go here, there's a train that goes all the way to the top, and the living quarters are probably 100 metres below the laboratory. So we live down there, that's where the scientists live during this time. And you can spend, between a month and 2 months up there. First of all, the altitude sickness gets to you, because it's quite high, air's quite thin up there. But eventually you start to get used to it. And what we do is we go up there, usually in the winter, we set up the instruments here, and we measure the properties of aerosol particles there, and we measure the properties of mixed phase clouds. We want to understand the structure of mixed phase clouds. So that will help us, if we can understand the structure, that will help us describe a weather forecast better. That's why we do it. And so, glaciers here, and it's also a tourist attraction, so tourists can go up there and visit the Jungfraujoch and walk around the platform here. They can't go up to the lab, but they can walk around the platform here while we're working up in the lab here. And what they can also do, 100 metres below, is you can walk through the glacier. So there are tunnels in the glacier, and so the scientists can do this too. Well, there's no one there. And so I decided to have a walk around the glacier one evening and saw a little guy, this guy, scrap from, Ice Age. So it's just a tourist attraction. Okay, so they've capitalised on this Ice Age cartoon, it seems. So it felt the Jungfraujoch featured in this film, The Eiger Sanction. And further upwind, there's another laboratory that we use, because what we want to understand is if there's aerosol particles feeding in to these clouds upwind, then how do they affect the clouds? If we can measure aerosol particles, we can measure their CCM activity in the atmosphere, and we can measure their IN, so ice nuclei activity. And we can somehow do a budget study to say, well, if that's the aerosol particles feeding into the cloud, and these are the properties of the cloud that we might expect. So we measure upwind as well. And upwind, there's another laboratory that we use, which is called the Schilthorne site, and this also featured in a film on Her Majesty's Secret Service. Okay, so another very famous film, James Bond. Anyone seen this film? Some people maybe seen this film. Okay, so James Bond's a bit more famous than Clint Eastwood maybe. Okay, so this is the rotating restaurant further upwind, and this is where we tend to measure the aerosol particles. It tends to be below the cloud, before the air has entered the cloud. And you might imagine that the restaurant is quite an expensive restaurant. It rotates. It featured in this film on Her Majesty's Secret Service. But I wasn't too impressed by the quality of the food when I was there. It's the kind of thing that you can get. Burger and chips. Okay. 007 stamp on there. But no, it wasn't too impressive. Okay, so this is the Jungfraujoch laboratory right at the top of this mountain in the Swiss Alps. as I said, the platform here where we measure, the observing platform here where tourists can walk around and look on the side of the mountain, and we measure both aerosol particles and cloud properties at this site. So these are aerosol inlets, which tend to be on this platform here for some reason. Doesn't matter where they are, it's just that it's convenient, I guess, for power requirements to have them there. So aerosol inlets, all these special inlets that can suck in the aerosols, and attached to these inlets are instruments that can characterise the aerosols. So we measure biological aerosols, we measure dust particles, we measure black carbon aerosols, so like smoke particles, and we measure volatile aerosols too. Okay, so it's all measured through these inlets. This is Manchester's bit, so this is a rotating measurement platform that we assemble, and here we're measuring cloud droplets, and here we're measuring ice particles. It rotates into the wind, so we can measure the aerosol, the cloud particles as they get sucked in through these instruments. So I just want to show you some of the measurements that we get on the cloud side. So I've been talking about supersaturation, I've been talking about fluctuations in turbulence and how that affects the supersaturation. Well, these are quite common measurements that we see now. So there's a few acronyms on here which we'll try to explain. Okay, so CPI, that means a cloud particle imager. The cloud particle imager is this gold instrument here. It's basically a cloud camera. So it takes pictures of cloud particles, and then we use some algorithms to say whether those cloud particles are liquid or whether they're ice particles. Okay? So we do some image analysis there. And then we classify the images into spherical particles, SPH, and then different kinds of ice crystal. So there are algorithms out there that do this, that we've developed. Columns, stellar, dendrites, GPL is gropal, that's like soft hailstones, and then SIR and VIR, that's small irregular and big irregular. Okay, so for want of a better acronym. But what we see is that most of the ice crystals are in the small irregular category. So this is against time, and this is the number concentration, so the number of counts of different kinds of particles. So you see, the interesting thing is you see these transitions go from being liquid to ice to liquid to ice and so on. And these are coincident with an increase in vertical wind. Where we see the liquid is where we have the increase in vertical wind. So that ties in with what I said about the supersaturation. The supersaturation depends on these three terms. So we've got a term that depends on the vertical wind, first term, and then we've got terms that depend on the condensation rate or the deposition rate onto ice. Because we're seeing these vertical winds, you see that's where we see the liquid water. So the other two plots are just different ways of showing the same thing. Ignore the bottom plot, doesn't really show it that well. But the cloud particle imager, so this is the same data but shown a different way. So we've got time along the x-axis here, and then we've got the size of the particles in micrometers, we're going up to 250, and the colours, the number concentration, how many of them there are, reds being a lot, blues being not a lot. So you see where you have the droplets, you have lots of small particles. Where you have the ice crystals, that's where you see the large particles. So it's just a different way of showing the same thing. So the raw images from the cloud particle imager look like this. You can see these are the ice crystals, and we see a very sharp transition to liquid. Mostly liquid, with maybe one ice crystal there. But these spherical particles are liquid particles. And then a very sharp transition again, going into the ice. Okay, and these are coincident with the vertical wind. So really this is just another way of showing the plot that I showed you yesterday, which was that layer cloud observed with LiDAR, so remotely sensed rather than in situ, and showing liquid water at the top with ice falling out. Because what's happening here is we've got the liquid water and we've got the ice that are separated. So the Bergeron-Finn-Dyson process can't really act in this case because the ice crystals aren't really coincident with the liquid water. So when we think about Bergeron-Finn-Dyson, we think about ice and liquid being mixed together. And in that case, that's when we expect the ice to grow and the liquid to evaporate. But here, you can see these very definite transitions between all ice and all liquid. So it appears that there's some structure to the phase of the cloud. There's some small scale structure which is quite difficult to represent. So yesterday, that was the equation that I wrote down. Didn't really derive it, but the important point, if you want to derive it, you don't need to, is to just write down the equation for the supersaturation and then to differentiate it. And the rest is just algebra, substituting different things in so that you get this form of equation. So you have these three terms. You have the expansion and cooling, so the vertical winds. Positive vertical wind gives us a source of supersaturation, and we've got these two terms which are related to the condensation. Condensation onto liquid, condensation or deposition, as it's called, onto ice. So what I want to do now is to try and understand this equation a bit more. We can't integrate this analytically. So there's no way of integrating this equation analytically yet. If you find a way of doing it, let me know. But there's no way of doing it as yet. So, if we want to integrate it, we have to do the integration numerically on a computer, or we can look at limiting cases. Now, because this course is assessed via an exam, I'm not going to ask you to integrate this numerically. So I will ask you to look at limiting cases. And the limiting case, by limiting case, what I mean, what we're going to do is we're going to set the left-hand side to 0. So we're going to set the rate of change to 0. So that becomes a 0. And then in that case, we get this form of an equation. So we've still got the source term here, first term. Second term, the other thing I've done here, so we've got the term in brackets, and for the rate of change of liquid water content or mixing ratio, I put in the number of droplets times the growth rate of those droplets. So this is the Maxwellian growth rate. So we derived that, I think, in the third lecture or fourth lecture. Third term, same, but for ice. And for ice, I'm saying that these are spherical ice particles, so the capacitance is the radius of the ice particle. So it's just this geometric factor. Remember, we have the same form of growth rate. It looks slightly different. Now, the reason why it looks slightly different is because the supersaturation here is expressed in terms of the supersaturation of a liquid, whereas the growth rate of ice is proportional to the supersaturation of ice. So that's all that is. And A1 and A2, they're just constants in the denominator, quasi-constants. They depend on temperature and pressure, but we can treat them as constants. So if we do some rearranging to find SL, so to isolate SL on the left-hand side, what we find is an equation that's called the steady state supersaturation in a cloud. steady state because in order to find this equation we had to set the derivative on the left hand side to 0. So it's a steady state. And looks like this. So we've got a term that depends on the vertical wind. We've got a term that depends on the number of ice crystals and the size of those ice crystals. And then the denominator, we've got the sum of something that depends on the number of liquid droplets, the size of the liquid droplets, the ice crystals, number of ice crystals, and the size of the ice crystals. Okay. And these parameters, A0, B1, BL, B2 and so on, treat those as constants, they're quasi-constants. They depend on temperature and pressure, but we can treat them as a constant. So that's the steady state supersaturation. So I want to go through some examples now of how this all works. So why I bothered doing that. So I'll switch to the visualizer. So we'll go through an example now. Do I do main page, visualizer, display? Yeah. So the steady state supersaturation. Okay, so we end up with something that looks like this. SL, just write it down again. Now I've called these constants slightly different things. I've called the first one alpha times W minus, we've got gamma times N ice. This could be the capacitance and delta. So I've separated this constant out into two. There's a reason for doing that, we'll see in a minute. And then divided by beta N drop times the average radius of the drops gamma N ice. Okay. Something like that. So that's the steady state supersaturation. That's the important equation. So now I'm going to do an example. And hopefully by doing this example we'll understand how the supersaturation works in a mixed phase cloud. So the example is, we've got a situation where the temperature in a parcel of air is 258 Kelvin. Could be anything, but I've chosen 258 Kelvin. And the pressure is 500 hectopascal, which is 500 times 10 to the 2 Pascal. And we've got a cloud at these conditions with a vertical wind equal to 1 meter per second. So that's the vertical wind. Means it's cooling. Positive means it's cooling. And we've got a number of cloud drops, and I'm going to pick a typical value for the cloud drops equal to 100 times 10 to the 6 per kilogram of air. Now if you think about a kilogram of air, let's just think about the number of cloud drops. A kilogram of air is approximately a metre cubed at the surface, because the density of air is about 1 kilogram per metre cubed approximately. So number of drops, 100 million per metre cubed roughly, and this works out at about 100 per centimetre cubed. So a little centimetre cubed, we have 100 droplets. That's a typical value for a cloud, 100 droplets per centimetre cubed. So I've chosen typical value, cloud droplets, and the radius of those cloud droplets, this is perhaps a bit large, 30 times 10 to the minus 6 metres. So this is actually quite large. It helps me with the example, that's why I chose it. So 30 times 10 to the minus 6, 30 micrometers, 30 mu meters. And so now we're going to say, I've calculated, so if you think about an exam question, I wouldn't expect you to calculate these quasi-constants, you'd be given them. So I've calculated these quasi-constants for you. Alpha, for these conditions, alpha is about 6.6 times 10 to the minus 4 per metre. Beta is about 3.1 times 10 to the minus 4. Units are kilograms per metre per second. Doesn't really matter what they are as long as they're in standard units. Gamma 3.1 times 10 to the minus, same again, 10 to the minus 4 kilograms per metre per second, and delta is about 0.1375. So those are the initial conditions. Now we start with a question. So part A, I'm going to say, in these conditions, what is the steady state supersaturation? Okay, so that's fairly straightforward. We just substitute these values into the formula, and I've not talked about any ice crystals being present, so the number of ice crystals just set to 0. So in this case the formula becomes SL equals alpha W over beta and drop A, and if you substitute those values in, you'll get something like 7 times 10 to the minus 4 for the steady state supersaturation. So that tells us that the supersaturation of a liquid just sits slightly above 0. So it's always slightly supersaturated. Okay, and that makes sense because we've got cloud and we've got a source term, which is the vertical wind, the cooling of the parcel of air as it rises. And if that's the case, if the parcel's cooling, if it's cooling, then what must happen is, if we go from time 0 to time 1, what must happen is we must have some condensation. And for condensation to happen, we need a supersaturation. We need a small supersaturation to drive the water molecules to the drops. Okay, so that's a fairly straightforward example. Now B, I'm going to say now, so if we go back to the Clace example, the droplets there were about 30 micrometers. I'm going to say B, number of ice crystals now, I'm going to add some ice crystals in, equals 10 to the 6 per kilogram. So 10 to the 6 per metre cubed, roughly, or 1 per centimetre cubed, which is quite high for ice crystals. But you always tend to find that the number of ice crystals is lower than the number of drops by a significant fraction. So here we've got 100 times less ice crystals than drops. And the size of these ice crystals, so again you saw from the Clace example that the size of the ice crystals was much larger than the drops, typically a couple of hundred microns. So I'm going to say the size of these is about 200 times 10 to the minus 6 meters, 200 micrometers. Okay, so the question again is, what is the steady state supersaturation, and explain what it means. So explain what happens. So I'm going to calculate it now. So it's the full formula: alpha W, alpha n ice, sorry, gamma n ice C delta divided by beta n drop A plus gamma n ice C. And if you substitute those values in, you get minus 0.079. So what does that mean?
It's nothing.
Say again.
It's nothing.
So what's going to happen to the cloud? So it's not saturated. So what will happen? I mean, this is the steady state supersaturation. So if we think about time t equals 0, this example, what would the supersaturation be? Would it be this? What do you think? Would it be greater than that? Or less than that? Time t equals 0. We've got a cloud, we've got drops. Supersaturation is quite a difficult concept to get your head around. Otherwise, I'm going through it now. So, what do we think? So what have we calculated? So this is a third year module. I'm not going to ask you to just calculate something and not tell me what you calculated. I want you to think about what you calculated. And what it means. That's the important bit. Anyone can plug numbers into a formula. What do you think?
Ice grows.
Ice will grow? Okay. Will liquid grow? What will the supersaturation be? Is that what the supersaturation will be at the start? Is that what that means? So we've got two situations. We've got time 0 and we've got some time in the future. You've just calculated supersaturation, or I've just calculated supersaturation. What will the supersaturation be at the start, time 0? What do you think? Did you say it?
Greater than 0. Top A.
Greater than 0.
Answer.
Probably somewhere near the top answer. Why?
Because there are more drops.
Because we've got drops. We've got drops. It's got to be at least at saturation until the droplets evaporate completely. So what happens here, what could happen, I might ask you to sketch a diagram of what happens, because that's important to think about. So if we think about time, and we think about the supersaturation of a liquid, so we could have the situation, this is minus 0.079. So we could have two situations. We could have a situation where it goes down like this, and the minus 0.079 is the steady state. So this is an asymptote. Do you all know what an asymptote means? It means it tends towards this line. The other situation is that the supersaturation remains fairly constant, close to zero for a time, until the liquid water is completely evaporated, and then it comes down and asymptotes to this line. Which one do you think is the right answer? Is it this one, or is it this one? It's the second case. It's the second case. So what you need to be able to do is to explain why. And the reason is, if we have droplets, they're fairly large in size, 30 micrometers in size. If the supersaturation drops a little bit below zero, then the droplets will start to evaporate, and because water is conserved, when they evaporate, it goes into the vapour phase and increases the supersaturation. It tends to stay at a saturation ratio close to 1, supersaturation close to 0, until the droplets have shrunk to a size where that water reservoir has completely gone. And then it can start to come down to this asymptote. So that's how a mixed phase cloud like this would behave. Now the second or third example, so that was B. So we'll do C. So we're going to increase W to be 25 meters per second. So let's just see what happens, and the answer you get is that SL is 0.08. So I should have said in this case, case B, the cloud glaciates. That's the eventual steady state. Glaciates means that the phase goes to the ice phase. The phase of water goes to the ice phase. In case B, exactly the same, except we've got stronger updraft. The cloud does not glaciate. Alright, so you can see stronger updrafts can maintain liquid water. Now this is why layer clouds, the thin ultraviolet layer clouds, do not produce lightning, and thunderstorms do. I said to you that the charge transfer process in thunderstorms needs to have liquid water present. You need ice crystals and liquid water. And the only real way you can have that happen is to have these high updraft speeds that you get in thunderclouds. So a thunderstorm, a cumulonimbus cloud, which has large vertical wind. In the last PowerPoint, I didn't show it, but in the last PowerPoint from yesterday, there's a time-lapse video of a thunderstorm from Australia. So if you're interested, you can see how that grows with time. In that thunderstorm, the maximum vertical wind measured in that thunderstorm, using Doppler radar, is about 45 meters per second. So 45 meters per second vertical wind. huge. Okay, so you can imagine that that thunderstorm remains mixed phase for a long period of time until the ice crystals grow to a size where they can deplete the supersaturation. And then final, D. So what I'll do now is I'll say, okay, what happens when we have W equals 0 meters per second? And we'll say N drop equals 0. So we've just got ice crystals in the cloud now. And in this case, we calculate that SL equals delta. You substitute the numbers in, you get SL equals delta, which is, or even minus delta should be, minus delta, there's a minus sign there, minus delta minus 0.1375. So the significance of this number is that at 258 Kelvin, at T equals 258 Kelvin, supersaturation of a liquid equals minus 1.375 is the value of ice saturation. So at 258 Kelvin, SL equals this is the value of ice saturation. So in other words, SI equals 0 at these conditions, to substitute in the formula that I showed you last lecture. So what happens in this case? What happens to the cloud in this case? We've got no liquid, number of drops is 0. We've got ice. What happens to the ice? It's fairly straightforward, this one. Supersaturation over ice is 0. What's going to happen?
Evaporate.
No, it won't evaporate. So the growth rate of ice, dm by dt, is proportional to the size of the ice, the capacitance, and the supersaturation.
So not consider the curvature effect.
Oh yeah, there's a small effect, which is the curvature effect. But ice crystals are usually large enough that we can neglect the curvature effect. So what I want to say is that the ice crystals, they won't grow or they won't evaporate. They've just completely gone to equilibrium in this case. So ice saturation ice neither grows or evaporates. Okay. So how did you find that example? Does it make sense? It makes sense now? We've gone through it? I think it's probably quite useful to do that. That's the kind of thing I'd expect you to be able to do and explain. Not just substitute the numbers, but to explain, what's happening to every phase of the cloud: the vapor, the liquid, the ice. Okay? Good. So just to finish off then, let's go back. So just very quickly, so there's some more examples. Good. There's some more examples here. This is the actual integration of that supersaturation equation. And you can see what happens with time is the supersaturation approaches at some steady state. It starts to asymptote to a value. And this is just showing that if we calculate that steady state for a liquid-only cloud, this is supersaturation on the x-axis against height. If we calculate the steady state, we get approximately the same answer. So we've got blue 10 meters per second. If we calculate the steady state supersaturation, we get 0.0015, and we can see, yeah, it is starting to go down there, but it takes time to get there. And then for the 1 meter per second updraft, 3014, 1 meter per second, you can see it is does kind of work, which is good. Showed you this graph yesterday. So this is the turbulence maintaining mixed phase clouds. So if we had no turbulence, then all of the liquid water evaporates and the ice crystals grow until we can have no more growth. If we have turbulence, then we can maintain mixed phase clouds. Okay, so this is kind of what this is shown in the observations. So you've seen this with the LiDAR plot yesterday and the radar from Chilbolton, and we've seen this in the observations from the Jungfrau Joch laboratory I showed you today. Over the next few days, the weather's going to get quite exciting. A little bit of rain, warm front followed by a cold front. So if you're looking Wednesday evening, Thursday morning, something like that, that's when we should expect the cold front to come through. Now, ahead of the cold front, so before the cold front gets here, you may want to have a look. Just go into Google and Google Chilbolton, written in the slides, Chilbolton data plots, and you'll see these LiDAR plots, and you may see some of these mixed phase layer clouds with liquid water at the top and ice crystals falling out of them. So over the next few days, sort of late Wednesday, early Thursday, you should expect to see that. So if you're interested, you can go and Google that. The final thing, so what I've shown you is fairly recent stuff that people have started to look at, weather organisations, and there was a recent paper, 2016, a physically based subgrid, it's a bit of a mouthful, subgrid parameterisation for the production and maintenance of mixed phase clouds in a general circulation model. And this paper had a couple of case studies. So it had a case study in the Arctic, and what they were looking at was the surface downwelling long wave flux. Okay, so this is downwelling long wave flux, how much long wave radiation can get to the surface against the liquid water path, how much liquid water is in the cloud. And we had two experiments. One, just a standard case, so this is like what the weather forecast models do presently with liquid water and mixed phase clouds. And then two, an experiment. And the experiment was included in the supersaturation equation that I've just shown you. So the steady state supersaturation in the cloud in the weather forecast model. And what they did was use subgrid turbulence. So they have these ways of representing what goes on below the grid scale in terms of vertical wind, and they use that subgrid closure of the turbulence, how they represent turbulence at subgrid levels, to say how much mixed phase cloud there should be. So it's kind of like saying we've got a PDF of updraft speeds, a PDF like a histogram of updraft speeds, and then I'll sample that histogram of updraft speeds to see what fraction of the grid should have mixed phase clouds. And so the green lines are that model experiment, and these green dots are the observations. So you can see better beginning with the observations for this Arctic case study. So that seems to be doing a good job there. The other place where climate models have massive bias in the results, so they can't represent reality, is in the Southern Ocean. So there's problems in various places, but there's a huge bias in the Southern Ocean. So what this is, it's a global map, latitude, longitude, and it's a climate model simulation from the Met Office, minus some satellite data from the Ceres satellite. And you can see this massive bias in the Southern Ocean clouds here. And the reason for this is that in the model, once we have ice in the model, the clouds in the Southern Ocean glaciate. So they don't have the right long wave flux. So we have this minus 40 bias in the Southern Ocean. Now, what they did in this paper was to repeat the simulation, but include this parameterization with the steady state supersaturation equation. And although it didn't fix the problems in the Southern Ocean, it did improve them a little bit. So this bias now is a little bit less red. You're looking at maybe an average of minus 20, minus 30 watts per meter squared in the Southern Ocean clouds versus minus 40 to minus 50 being the bias. So it seems to have fixed some problems, not all of them. And we're currently looking into fixing that problem, what's causing the extra bias in the Southern Ocean. I think it might be something to do with aerosol particles. Okay, so main points: liquid only cloud, upward vertical motion, the air will be supersaturated, so we calculated that small supersaturation. It's proportional to the updraft speed, it's inversely proportional to the first moment of the drop size distribution. So we've got the term that depends on W and divided by the first moment of the drop size distribution. Ice cloud with no vertical wind, then the steady state is for ice saturation. Ice neither grows or evaporates in this cloud. Ice cloud with upward vertical motions,